my name is Seth Kinoshita, and this is Lab 1 of Physics 2211, Constant Velocity. The purpose of this lab is to observe the motion of an object at constant velocity and compare computational and experimental analysis of the object. Before I get into the procedures of the lab, it is important to understand the physics principles behind it. The main principle is Newton's second law that most people know as F is equal to ma. However, that is not the only way to express this fundamental law. It can also be expressed in terms of momentum, seen here. Assuming that mass remains constant throughout the experiment, we can divide this whole equation by mass to give the velocity update formula, where acceleration is defined simply as net force over mass. And the main idea of this lab is that, ignoring any frictional forces, an object moving at constant velocity has no net forces acting on it. Therefore, the a delta t term here, where acceleration is defined as the net force over mass, goes to 0, and you are left with a statement that final velocity is equal to the initial velocity. This also builds on Newton's first law that states an object in motion will stay in motion unless acted upon by an unbalanced outside force. Without an outside force acting on the cart, it should stay in constant velocity. A fundamental physics error of this lab that we must understand is that while we can ignore frictional forces computationally, they still do exist in the real world. This free body diagram here shows that what we are assuming in this experiment, which is that there are no net forces. But the frictional force shown here is likely much larger and results in less than constant velocity for the cart. The actual experiment was performed by setting up a video camera and recording the motion of a cart for a certain period of time. Tracker was then used to find the position at each frame during the interval, shown here. A portion of the final results are shown in the graph in the top right. Some initial conditions that were determined included the cart as the system and the surroundings as the track and the earth. The initial position was set so that the axes put the cart at the origin, and the initial velocity was calculated using the first two data points from Tracker, seen in this formula right here, where velocity is calculated as the change in position over the change in time. The positions on the x-axis were used, and the change in time was 0.017 seconds, resulting in a final velocity of 5.59 meters per second. This initial velocity is only in the x direction as there was no y or z movement to the cart, so the initial velocity vector can be shown like this. After these conditions were determined, I used the skeleton code to model my cart computationally. I estimated the cart's mass to be 500 grams or around 0.5 kilograms, and set the initial position and velocity vectors described on the previous slide. The change in time, 0.005, was determined using 1 over 200 because the video was recorded in 200 frames per second. Since the total time was around 0.25 seconds, the loop was only going to run for that amount of time. The velocity update formula was applied in addition to the position formula, where the velocity update formula is here and the position update formula is right here. The net force vector was assumed to be 0, 0, 0 because I'm trying to model an object in constant velocity, barring the presence of any frictional force. And here's what it looks like when I run this code. And then using these results, I created a graph of a computational model where the computational data and the experimental data were put on one graph. So the experimental data you can see in blue and the computational data you can see in red. As you can see, they are pretty similar, but the experimental data does have a horizontal position less than the computational model at some points. This is a good indicator of the fundamental error mentioned earlier about ignoring frictional forces. A lesser position across the same time interval indicates that velocity decreased at some point, indicating an outside force opposite the direction of motion, otherwise known as a frictional force. On to some conclusion questions. If the axes were flipped, time would still progress in the positive x direction. However, positive position values would now be negative, meaning the graph would be reflected over the x-axis. The assumption that net force is equal to 0 is likely not accurate, seen in the comparison graph. There will almost always be frictional forces acting on motion, whether it is from or from air resistance. This leads into the next question: which is, can we say how many pushes and pulls acted on the system to give a net force of 0? No. Each individual air molecule and each individual molecule on the track can resist motion, meaning that there are way too many pushes and pulls that contribute to a theoretical net force of 0 to give a quantifiable answer. Thank you.